So here's tutorial 4 on the COVID-19 project. This is where we get a bit more technical using TI-Nspire and Desmos and start to model data. So in the last tutorial, video 3, we actually had this data here. We plotted day against total cases, and we got this nice graph down here. We didn't tidy up the title, but that's okay. We can do that in any presentation. And we got this data set as an XY scatter graph, and we tried to fit the best model. And our best model looks a little bit weird. We had this thing here, you can see that in the highlights here, 304e to the power of 0.233x. Now e is a special number, it's 2.718. So this is kind of a little bit weird because the model we were expecting was something like this, an exponential model. This is an exponential model, but given in quite a different form. So if we have a look at this one here, 114 times 1.33 to the exponent d. So these numbers are all pretty significant, and the tie-in with the data table we've used. Look, the 114 is the number of cases after day 0. So if d is 0, if you substitute d as 0 into here, 1.33 to the power of 0 is 1, and you get t equals 114. Okay, so that's the number of cases after day 0. The 1.33 you can clearly see is meaningful. The 1.33 is the multiplier. So it's here, it's the average multiplier. So 114 times 1.33 to the power of 1, to the power of 2, to the power of 3. You can kind of see how this model is formed. Okay, so this makes sense. This model is the automatic fit for the for Google Sheets. And as we said, maybe at the end of the last one, it might not be the best looking model because it's hard to unpack and interpret it unless you're really familiar with E and the number and working with exponents. Okay. So what we're going to do is we're going to duck out of this particular package and we're going to look into a different package and see how other bits of software handle this and to see if it comes up with a more usable formula here, okay? So what we're going to do is we're going to just click, we're going to highlight all of the data, 0 down to 20. Remember there's only the first 20 days, and down here we've got more days all the way up to 34, that's the 6th of April. By the time you watch this video, it's going to be at least 1 to 2 weeks beyond that. But you can obviously update the model with new, fresh data as long as you're using reliable data. So back to here, I've highlighted all this, and I can go to 2 bits of different software. The first one is your TI-Nspire. Now, if you don't have an online TI-Nspire student software, you can actually download for free now from TI-Nspire. They're offering a 6-month free deal, so I'd highly recommend going to that. So here we're in a document, we're going to insert a spreadsheet. And sometimes if I just paste straight away, sometimes there's a gap missing. So sometimes I just click another cell, click back to where I want to paste, and then Command V. So Command C, Command V. So this is D, day, and this is T. Okay, no need to capitalize. And that's it. We've literally transferred the data from our spreadsheet straight into a different graphing software. And so now we're going to go Document, Insert. We want a graph, but the graph is about data, so it's always data and statistics. Click on the variable, choose your variable, days. Click on the y-axis, choose your variable t, and you've got your beautiful graph here. Okay. Obviously, you can do a screenshot and paste that into a word processing document or Google Docs. But now we're going to try and do the best fit from here. So we go to Menu because we want to do something with it. We're going to analyze this graph, and we are going to fit a regression line on it. And look at all the options we have here. You can see the best option we're going to go for is exponential here. And when we fit the exponential, okay, so this looks like a graph in a bit of a more user-friendly form. So if we look at this, the y values, the total number of cases is 256 times 1.24 to the exponent x, the number of days. Now that ties in really closely, look, with our previous model by hand, 114 cases times 1.33, so multiply of 1.33. TI-Nspire has changed those numbers. Instead of a 1.33 multiplier, it's changed it to a 1.24 multiplier, okay? So instead of 33% growth, it's a 24% growth, okay? But now just looking at it visually, it's quite interesting, isn't it, to see is it a better fit than the actual graph that we had originally. And again, this is just a visual eyeball just to see what might be happening. Okay, so there's one way of getting a different model using TI-Nspire, and we're going to come back to the TI-Nspire, but we're going to take that same data. I've still got it copied on the clipboard, I think, but I'm going to go back here I'm going to copy it again from just the data. We don't need the headers here, Command C, and I'm going to open a new tab, and I'm going to go into Desmos. I'm going to do the graphing calculator, and we're just going to literally Command V it. Okay, so it plots it as a data set here, which is kind of cool. And there it is. Make it a bit nicer for you, projector mode, so you can see it in a bigger detail. Now over here, it's got x1, y1 for data. Now, there's no automatic click a button and fit an exponential model, but you can craft it by using the following, okay? So we want, the data is y and x here, but look, it's x1 and y1, so we have to use those variables. So we're going to say that y1, so just type in y and 1, then get this keyboard out, press ABC, and it's this little squiggle here, okay? This mathematically means it follows, y1 follows the following model, okay? Or y1 can be approximated by the following model, okay? And we are going to just type in really the structure and the layout of the previous one that we had here. Look, a number times by multiplier to the power of the number of days. So a number times multiplier, and that's what we got on TI-Nspire as well. So if we go back to, okay, so a number times by the multiplier to the x. Go back to Desmos, and we got to type in the model we want to fit. So a number, so I'm going to put maybe S for the starting amount. I'm going to put times by m, the multiplier, and then we're going to exponent it. This is a to the b on the keyboard, to the x of 1, okay? And if I just put the keyboard down, so Desmos has fitted also a nice looking model to it, okay? And Desmos chose the S number to be 472, and the m, the multiplier, to be 1.23. So this is a 1.23 multiplier, 23% growth. The one we did by hand was a 33% average growth, and TI-Nspire was a 1.24, 24% growth. So they've gone for slightly different values here, haven't they? Okay, so it's interesting, isn't it? The different software produces different models, so that's something to be aware of, isn't it? Okay, so now we want to know, well, which is kind of the best model, and that's really a hard thing to judge, because these models are only designed to fit the first 20 days. So each bit of software has produced what it considers the best model to predict the number of cases, but only for the first 20 days. Each model may have big failings if we try and predict beyond 20 days, okay? So a test of how good is this model? Well, the model fits the first 20 days probably pretty well, because we've asked the technology to fit the first 20 days, but then how well does it fit the days beyond 20, okay? So we're going to test each of those models in two ways. One, how well does each model fit the current data for 20 days? So that's the first thing we're going to do. But then we're going to make a prediction and say, well, if we use each of those different models, how well do they predict the future? And that's always very dodgy when you start predicting the future based on a model that's only shaped by the first 20 days of data, okay? So the first thing we'll do, let's go back to Desmos. Okay, now Desmos has got a nice little thing called residuals here. So residuals, when we see it, and can you see we've plotted them, and these are the residuals. So what is a residual? Well, let's just click on one and have a look. Click. This is 17. So this is day 17, and this little red residual is 1056. Okay, so day 17 is here, day 16 is here. So day 17, if you look up here, on day 17, the model predicts a certain value, but the actual value on day 17 is just a little bit bigger. So these residuals are the actual data for day 17, subtract the model's prediction for what would happen on day 17. Okay, so the residuals literally tell you how far is the actual data away from the predicted data. Okay, so these are the residuals here. On day 20, the residual is negative 1,400. Okay, but then we are in the 20, 30,000s here, so maybe 1,000 sounds a long way off the prediction, but this is 1,000 in terms of 30,000. So as a percentage error, maybe it's not so bad. So this is what residuals do, and you can have a little look at those. There's another measure of how well the model fits the data for the first 20 days, and it's called an R-squared value. So here the R-squared value just is a number between 0 and 1. The closer to 1 it is, the better the actual model that you've created fits the data. In fact, if the R-squared value was 1, then all of these points would be perfectly on this curve. Okay, so this is R-squared is very, very close to 1. Okay, so let's go back now to TI-Nspire, sorry, we're in Desmos there, and let's see what the R-squared value and the residuals might look like here. So if we go menu here, and we look at the plot properties, we can actually have a little look down the bottom here and add some extra, but it's not on that menu. Just give me a moment to find the right menu. I'll press escape, and I will analyze again. And under the analyze menu, it's on the residuals here, okay? So if I show residual plot, you see it does a similar thing. Now for the first 20 days, 0 to 20, these are all the residuals, okay? Now it's not as clear cut as the Desmos because it's not as big a screen, but here's 20 days. Now at 20 days, the residual is 10,000. Now I'm sure at 20 days, the residual on Desmos was a lot less. But if we go down here, the residual at 9 days is 408. So it's just a visual comparing how far away is the model from the actual data. Okay, so there's the residuals. But then on Desmos, we have an R-squared value. And remember, the R-squared value closer to 1 is the better the fit is. So this is really close to 1.9926. And then on TI-Nspire, can we find an R-squared value? Well, on this page, no. But if we go back to the data, click in the first spare cell after the data you've put in, menu, we will do statistics, we will do a stat calculation, and we will do a exponential regression. So we're going to get the same formula for the best fit model coming out, but we'll also get a few extra things. The X list was the days, the Y list was total number. Press OK, and down here we've got an R-squared value. So this is 256 was the starting number of cases at day 0. 1.24 was the multiplier, 24% growth, and the R-squared value is 0.946. And the R-squared value for your Desmos was 0.9926. So according to the R-squared value, the Desmos model is a better fit. But remember, that is only for the first 20 days. So what I'm going to do next is I want to see just how well these models work when we move beyond 20 days. Now you have to be really careful when you use a model to predict beyond the data from which it's been formed, but we're going to do it here just as a little check, okay? So we are going to see that according to this model on Desmos and this model on TI-Nspire, we've currently got in the realms of 30,000. What do the models predict for 200,000? Okay, so on Desmos, I'll go y equals 200,000, okay, and I will just zoom out here and zoom out. But can you see as you're zooming out, you're kind of losing a bit of clarity here. So a better way than zooming out, I'll zoom back in and zoom back in and move this across a bit to get the detail. Maybe a better way is actually to click on the spanner here and just change these manually. So the days I'm going to go up to maybe just 40 days, and the y-axis I need to go up to, as I said, 200,000. So let's go to 220,000. Okay, so it brings it into a better frame of mind. So click on the point here and you see, look, according to the Desmos model, we hit 200,000 after 29 days. Okay, now let's go to TI-Nspire and have a look at TI-Nspire and see what we can do here. Well, if we go up to, in this particular box here, we did save the equation, some residuals there, we saved the equation to F1. So you could go to your function plotter and get an idea here, but I'm going to keep this a bit simpler. On this here, I think I would like to menu, analyze, I'd like to hide residual plot, I want to go back to here, and I'm just going to drag this down until I see 200,000 appear. I'm going to go to Menu, I'm going to go to Analyze, I'm going to plot a function, and it's going to be f2 equals 200,000. Okay, and I'm just going to eyeball this really. Okay, I can get the exact intersection point, but not quite on this menu. But you can see just by eyeballing here, this is about 31, 32 days, something like that. So the model tells me I'm going to hit 200,000 after 31, 32 days. So there's a comparison between the two, 29 days versus 32 days. But of course, you can see the big problem, can't you? The actual data we already have. And 200,000 people, if I go down here, this is 130,000 here. So we're only at 130,000 after day 34. And both models predict we're going to get to 200,000 after days 29 to 32. But we've already got that data to account for, and we haven't even passed 100,000 by those particular time frames. So you can see that using the models to predict beyond 20 days is fraught with danger, and so mathematicians have to constantly refine models. So let's have one final look at why the problem kind of arose. The TI-Nspire models assume a 24% growth rate. Okay, so the number of cases increasing by 24% every day. Okay, and the Desmos assumed, when we fitted the best model, Desmos assumed, can you see M here? M here is 1.23, a 23% growth rate. So 24% and 23% growth rate, both models, Desmos and TI-Nspire, had similar growth rates. But of course the problem is, that's not so accurate, because for sure, 32%, 32%, 31%, all of these multipliers are changing. The average was 1.33. But look what happens if I just copy all of these multipliers, Command C, and go to the data set down here, starting at 1, Command B. And now we've got all this extra data. If I double click, look what happens after 20 days. 20%, 18%, 14, 13. The percentage increase is really coming down until such a state where we're in single figure percentage changes. So in the later stages, Spain's number of cases is only growing by 8%, 8%, 7%, 6%, 5%. Okay, so by assuming the model that we had for 20 days, we're thinking it's going to change all the time by 20%, 24%, 23%. So we have to try and adjust our models somehow. As you speak to your teachers, they may have some suggestions for you about how we alter our models. But the big takeaway is technology is great to fit data, but the data can only be fitted that's given. So if you try and fit a model to the first 20 days, it'll give you the best model for the first 20 days. And all bits of software have given good models for 20 days, but when you try and use the model to predict beyond 20 days, it is fraught with disaster and inaccuracies.